So our next topic is minima and maxima, extremal points of scalar functions. And let's start with a definition. It's going to be precisely the same definition as the single variable one. We say that, I'm going to write the definition for two variables, and it easily generalizes to several variables, that x0 is a local minimum. And let me write in blue maximum. So the condition for maximum is going to be separate. Is a local minimum or maximum of fxy, of a two-variable function, if there exists a neighborhood of x0, y0, such that f at xy is greater than or equal to f at x0, y0. And for maximum, what's it going to be? Less than or equal to. And this has to hold true for any xy in that neighborhood. For any xy in the neighborhood. So does this definition make sense, compile, feel like the right thing to say to everybody? Yeah? A minimum is, if it's in a neighborhood, the values are always greater than or equal to. Okay? And maximum, vice versa. Okay. Now let me remind you, a quick reminder of the situation for single variable functions. Reminder. So how did we usually tackle this problem? How did we usually find local minima or maxima? We used Fermats Theorem, right? Fermats Theorem told us, find the derivative, set the derivative equal to 0, and then those are your candidates. Those are your suspicious points, the points which are candidates for being extrema point, and we usually call them critical point. It sounds like a very, big word, critical point, but reminds me of heart attacks, critical conditions. That's what we call them, right? So reminder, for f from R to R, single variable functions, we find critical points, points which are suspected as being minima or maxima, using by Fermat's theorem. Fermat's theorem tells you that if the function is differentiable, then at minima or maxima, the derivative is 0. So when you look for those points where it's a maxima or a minima, you look for the points where the derivative is 0. Okay? We find critical points by finding points satisfying f prime at the point equals 0. Do you agree? And there's an entire discussion of this, and you know that. First of all, not every point that satisfies this is indeed a minima or a maxima. It's just suspicious. It could be, for example, like a shoulder like this, right? How do you call these? No, so let's write it. But sometimes we find points like this. These are the points we're actually looking for, right? Where the derivative is 0 because it's indeed a maximum. Sometimes we find points like this, where the derivative is 0 because it's indeed a minimum. But sometimes we find points like this, where the derivative is 0, but it's clearly not a minimum or a maximum. Right? That's why I said shoulder. And how do you call these points? Right. They turn out to be inflection points, although an inflection point is defined differently. It's defined in terms of of concavity, right? Of the function being concave up on one side and concave down on the other side. But that's what they usually turn out to be, right? So that's one issue. And another issue is that not all the points that are extrema points satisfy this. For example, they could be cusps, right? You can have an extreme, like think of the function absolute value. The minimum is at 0, but it's not differentiable there, right? Do you agree? Okay. So there's the issue of imposters, right? Points that satisfy this but are not really extrema, okay? And there's the issue of seeking points that are extrema but cannot be found using this search method. Clear? Okay. The same thing is going to happen for two variable functions. It's just going to be a bit more complicated. So in two variables, for example, are we going to have situations like this? Yes, that's precisely going to be the situation where we have a local maximum, right? Something like this. Think of an upside down paraboloid. Okay, so this is going to be the analog of this case. Do you agree? And of course, there's going to be the, so here it's going to be, maybe you can think of the tangent plane being horizontal. Okay, and there's going to be this situation obviously as well, a local minimum where the tangent plane is like this, right? So those two situations correspond. Can we have something like this? Well, yeah. Think of, for example, a bench in the park. Okay, so we can have something that looks like this. This is an attempt to draw it 3D-ishly. Okay, is it clear what I'm drawing? Okay, so on all these points here, so do you understand what I just drew? Okay, think of a bench, a nice wooden bench in Central Park in New York. Okay, you sit on it like this. So all these points here have horizontal tangent planes, but they're not maxima. If you go in this direction, you go up. If you go in that direction, you go down. Do you agree? Okay. So all these situations have the two-dimensional analog, but there's something even more complicated that doesn't show up in single variable. But also, that's right, but also we can have something like what we call the saddle, okay, where in some directions you're going down and in other directions you're going up. So, for example, one way to draw the saddle is that Pringle-like shape. Okay, remember the saddle? So this point here, if you try to draw a tangent plane there, it's going to be horizontal, right? But if you go in these directions, you're going down, and if you go in these directions, you're going up. Okay? So it's clearly not a minima or a maxima. Do you agree? Is it clear what I'm saying? Everybody? Do you agree that this point in the saddle smells like a critical point, right? Because if you think what's going on at that point, the tangent plane is going to be horizontal. The partial derivatives are going to be 0, or the directional derivatives are going to be 0, okay? But depends on how you set it up, but the partials are going to be 0. But, however, it's not a minima or a maxima. Okay?
The interval? Like if we take the interval, it is a maximum, like depends on which interval we take?
Interval is not a relevant word to two variable functions. Interval is a very single variable sort of word, okay? But if you take a neighborhood of this point, a neighborhood of the point, remember the domain is down here, this is the graph of the function, take a neighborhood of this point, if you move slightly to one direction, if it's that direction, the values are bigger. But if you move slightly in this direction, the values are smaller. So it's not a minima or a maxima. Clear? Okay. So what we want to do now is find theorems that tell us, one, what is the analog of Fermat's theorem in two dimensions, for example? What do functions have to satisfy in order for us to call them, what do points have to satisfy in order for us to call them critical points? Which are the points that we're going to look at? And it's going to be precisely a Fermat-ish sort of theorem. They're going to be points where the partial derivatives are zero. Those are going to be the suspicious points. Okay? And then we're going to need tools to sort them out, to figure out, and that's going to be something along the lines of the second derivative test, to say which are indeed maxima, which are indeed minima, and which are imposters, which are points which are neither. Okay? And then we're going to need tools to study what happens like at points which are maybe not, the function is not differentiable. Or for example, at points which are endpoints. Remember, sometimes minima and maxima can hide at endpoints of the interval in single variable. Here we're going to need to find when the minima and maxima are not at endpoints but on the boundary of the domain. Endpoints of an interval, there are precisely two of them. The left endpoint and the right endpoint. But the boundary of the domain consists of infinitely many points. And the minima and the maxima can hide there as well. Okay, so that's where our discussion is going to take us. Okay, so let's start with some very simple examples. And the first examples are going to be such that we don't need any theorems. We just need to think a bit and figure them out. So example number one, consider the function fxy equals x to the power 4 plus y to the power 4. Question, does it have any minima or maxima, and if so, at which points? Go ahead if you think you know the answer.
At 0, it must have a minimum.
Okay, why? Why are you saying that?
Because that expression has to be positive.
Very good. So clearly there's a minimum. It's a local minimum, but in fact it's even a global minimum at 0, 0. Very good. Because this expression, for any x and y, this is a positive expression, except when both are 0, when it's 0. Does everybody agree to that? And to the argument as well? Everybody? Okay. Does it have a maximum? No. Why not? Right. At any point you take, suppose you say, hey, 5.5 comma pi is the maximum. No, because if you move slightly in the direction of making the x bigger, the value is going to be bigger, right? So it's not a maximum. Maximum has to satisfy that if you move in the neighborhood, the values can only get smaller. Do you agree? So no max. Good? What about this function? Example 2, fxy equals x to the power 4 minus y to the power 4. You can no longer say that it's always positive or always negative, right? It can actually be either. So that sort of argument fails here. But I claim that you can actually say everything about this function just by thinking. And let me tell you what you shouldn't be trying to do. You shouldn't be trying to imagine the graph. That's one thing you should almost never try to do in the context of two variable functions. It's only in very, very special cases where you can actually draw or imagine graphs. Okay? You have some... you're right. It doesn't have any extrema, no extrema. Why? What's the reason?
To make x as big as you want, but making y as small as you want.
Okay, so the more precise, that's correct, but that's kind of not a local statement. By saying you can make x as big as you want, you're not arguing why maybe in some neighborhood it could be an extrema. True that out there, when x gets bigger and bigger, the function's going to get bigger and bigger. But why can't 2, 3 be a local maximum? Maybe it is. Okay? So you need to somehow fine-tune that argument.
Can you say x equals to r times cosine theta?
Oh, convert to polar. I don't know, maybe. But you don't need to do that. It's really not necessary here. Okay? We're not calculating limits or anything. I claim that there's a very local argument, very easy argument, to say that no point could be a minimum or a maximum. Think of a point, xy. Suppose you claim that xy is a minimum or a maximum. If you make x slightly bigger, the value of f is going to get bigger, right? Because you're taking it to the power 4. Do you agree? If you make y slightly bigger, the value of f is going to get smaller because you're subtracting it. Do you agree? So any candidate for being a minimum or a maximum is not. You move slightly in the x direction, you make it bigger. You move slightly in the y direction, you make it smaller. Do you agree? So that's the reason for no point being an extremal point. Is that clear? Good? Okay. So that's these two functions. But clearly we're not going to be able to study all given functions just by means of these kind of ad hoc special arguments for them. We're going to need some more general machinery. And the first part of that machinery is going to indeed be Fermat's theorem. So I don't know if not in all sources it's called Fermat's theorem, but in fact it's the generalization of what's usually called Fermat's theorem in single variable. So here's the theorem. Here's this theorem. Assume fxy has partial derivatives. That's not a very restrictive assumption, but it does need to be satisfied in order for the theorem to hold. And whenever it's not satisfied, just like in single variable, when you have points where the function is not differentiable, you can use the theorem. You can't set the derivative equal to 0 if the function is not differentiable, right? So assume that it has partial derivatives. Then, if x0, y0, why then if? If x0, y0 is a local extrema, either minimum or maximum, then not f prime, two variable, df to dx at that point is 0, and so is df to dy at that point. So if it's a local extrema, both partials have to be 0 at the point. If f has partial derivatives in all of its domain. Okay? If it's the analog of being, well, not exactly. If. Okay? So this is clearly a necessary condition, providing the partials exist, but it's not a sufficient condition. We said that. For example, take the saddle. Okay? The saddle satisfies this, but it's not an extremum, that point in the middle of the saddle. Okay? So this is a necessary condition. So let's write this is the analog of Fermat's theorem. in single variable functions, and it provides a necessary but not sufficient condition. So points that satisfy this are going to be our critical points. Okay, we're going to find points where the derivatives are, the partial derivatives are 0, but we're not done. We're going to have to still argue some more in order to check if they are or are not indeed minima or maxima. Clear so far? I want to prove this theorem. I want to prove Fermat's theorem. And the proof is very, very simple. It actually relies on the single variable theorem. So proof. Suppose f has a local maximum. The proof for a local minimum is similar at the point x0, y0. Okay? And the idea of the proof shows up again and again and again in the arguments we're giving throughout this course. It's the idea, the very basic idea, of taking a two-variable graph of a function, slicing it along a specific axis, and what you get is a single variable function. Does everybody see that? Does everybody picture that? In general, take a two-variable function, okay, it's kind of like this sheet lying up here in the air, slice it along a specific direction, you get a single variable function. Does everybody see that? That's what I'm going to do here. So here's, let's draw the arguments over here on the side. So here's three-dimensional space. This is the y-axis, this is the x-axis, and here's this point, x0, y0, right? It's a point in the domain where the function has a local maximum. So the graph is going to look something like, here it's going to have that local maximum, and the graph is going to look something like this maybe. Okay, it's a three-dimensional graph, but okay, there's also stuff back here. Clear? So do you see this tent here, and the peak is over here precisely above x0, y0. Does everybody see that? Okay, so this is the local maximum. And what I'm going to do, I'm going to slice it. I need the y-axis a bit longer. So I'm going to look at a fixed y0. Here's y0. So all the points along this line have y0 as their y-coordinate. Do you agree? Do you see a line on the floor? And all the points along this line have y0 as their y-coordinate, and x varies, right? What does this line look like up in the graph? Let's maybe take another color. Up in the graph, we get that slice. We get the single variable function living above this line. We get something that looks maybe like this. And here it goes back here. Do you agree? So the orange thing is what lives above this black thing. It's along that line. Do you see? Do you agree? Okay? And so here's formalizing this. I'm going to define a new function, call it g. It's going to be a function of a single variable x. And the way to define it is going to be take this two-variable function, allow x to vary, but fix y0. y0 is that y0 where there's a maximum. Okay? So do you agree that the graph of g is precisely this orange curve? That's the graph of g. X varies, y0 is fixed. That's what I get. Does everybody see that? Okay, continue. Clear? Okay. What do I know about g? G is a single variable function, and where does it have a maximum? At x0. Okay, it's a function only of x, and when x equals x0, it has a maximum, right? Do you agree? So g has a maximum at x0. By Fermat's theorem, if g has a maximum at x0, then the derivative of g at x0 is 0. Do you agree? So by Fermat, the single variable theorem, g prime at x0 is 0. Right? At a maximum point of a single variable function, the derivative is 0. But what is g prime at x0? What's the derivative of g? What's the derivative of g with respect to x? Its variable. It's the partial derivative of f with respect to x. Do you agree? So g prime at x0 is precisely the partial derivative of f with respect to x times the inner derivative, right? This is a composition. So what's the inner derivative here? 1. So it's precisely df to dx at x comma y0, and evaluated at x0, it's precisely this. And it equals 0. Good? Clear? You should agree that this looks correct, both in terms of the writing of the abstract statements, one following from the other, but also in terms of the geometry. You should see with your eyes that if this is precisely the graph of f, this is the graph of f x y0, the orange thing is the graph of f when x varies and y0 is fixed, and the derivative at this point, the tangent line at this point, is precisely horizontal. Okay? Do you agree? An analogous argument in the y direction, if we allow y to vary and fix x0, would give us that the derivative of f with respect to y at that point is 0 as well. I'm not going to repeat the argument, it's the same thing. Okay? So similarly, df to dy at x0, y0 equals 0. And that's the claim of the theorem. Everybody good? Clear? Okay, let's quickly do an example. Let's do an example. So let's consider the function f of x, y equals x squared times y plus x times y squared minus xy. Okay? Do you agree that local arguments, like we had very function-specific arguments, like the ones we had for x to the power 4 minus y to the power 4, are already too messy here? Do you see that? The x's and y's appear in too many places, even though it's a very, very simple function in terms of the formula. thinking what would happen if we take a point xy and make x bigger. Well, it's bigger here and it's bigger here, but y is squared, and here we're subtracting it, so it makes it smaller. Can you see that that sort of argument is not going to be too convincing in this case? Okay? And when we see what the points that we find are, we're going to see that indeed it's a non-trivial situation. Okay? So let's use Fermat's theorem. Do you agree that this function is differentiable? It's a C1 function. It has continuous partials on the entire plane. So clearly it has partials in the entire plane. So the only points that could be local minima or maxima are points where the derivative is 0. Do you agree? Okay, so let's find them. So what is fx, the derivative of f with respect to x? 2xy plus y squared minus y. Do you agree that this is the derivative of f with respect to x? And this has to be 0. That's what the theorem told us, right? Let's take a peek again at this theorem in case you forgot. If it's a local extrema, look here, thanks, then both partials have to be 0. So we're setting the partials equal to 0, and we're looking at which points indeed satisfy that. Good? Okay. So here's fx, has to be 0. Fy, what is fy? It's x squared plus 2xy minus x. That has to be 0 as well. So a point xy is going to be a critical point, a suspicious point, providing it satisfies these two equations. Clear? So let's solve them. Let's see which points satisfy this. So I'm going to rewrite them. And this is a general statement, okay? The systems that you're going to get here are not necessarily linear, right? Depends on what the function was. If the function was not a linear function, there's no reason for these equations to be linear equations. So you can't use tools, very elementary tools from algebra, right? Like setting up a matrix of the coefficients and so on and so forth. You have to use more sophisticated tools, maybe separate one variable from one equation, plug it into the other one, or if it's 3 variables, you're going to have 3 equations, right? So it's always good not to jump at it, but take a step back and think. Maybe there's some very easy statement that you can say without doing too much calculations, okay? And if you and let the math talk to you, okay? Dialogue is very important, okay? So let's talk. So do you see that we can pull out a y as a factor from the first equation, making it y times 2x plus y minus 1 equals 0, right? And similarly, we can pull out an x as a common factor from the second equation. So we get x plus 2y minus 1 equals 0. Do you agree? Now we have two products. This is a product and this is a product. When is a product equals 0? Only when one of them is 0, right? So either y is 0 and x is 0. That's one point that's going to solve this. So the solutions, the first solution is going to be y is 0 and x is 0. That annihilates both expression and it's a solution. 0, 0. Do you agree? The second solution, suppose y is 0 here, but here not x is 0, but rather this one is 0. Okay? But remember, y is 0. So if y is 0, x has to be 1. Do you see that? Did everybody understand how I just found this solution? Good? Everybody? Okay. A third solution is going to be when x is 0 over here, satisfying this equation, but not y is 0 here, but rather this expression, but x is 0. So y is going to be 1. Good? And there's going to be a fourth solution, and that's the last one. There are only going to be 4 solutions, where both of these expressions in parentheses are 0. Right? And that's the only one we need to work just a bit more to find. So let's write the fourth solution is going to be generated by the system 2x plus y minus 1 has to be 0, and x plus 2y minus 1 has to be 0. Do you agree? That's the fourth solution. And those are all of them. Do you agree? Is everybody with me? Okay? And that's what I mean by saying, if you would try to solve this for y and plug it into the other, maybe you'd get the same thing. This system is not too complicated any way you look at it. But it's always good, and we'll see it in many examples, it's always good not to jump at it, but rather to think for a minute. Pause and think. You can, in many cases, you can save yourself a lot of unnecessary work. Okay? Okay, how do we solve a system like this? Now there's really not much to do, right? X is 1 minus 2y. Plug it into here. Let's do that. So x from this equation, x is 1 minus 2y. Let's plug it into the top one. So we get 2 times 1 minus 2y plus y minus 1 equals 0. Do you agree? Everybody with me? And what do we get? We get 2 minus 1, so we get 1. Minus 4y plus y is minus 3y. So 1 equals 3y, so y equals 1/3. And x was 1 minus 2y. Why did I write minus? No minus. X is 1 minus 2y, so x is 1/3 as well. So that's the fourth point. Good? Clear? So does everybody agree that these are not all minima or maxima? These are the critical points. These we still have to somehow sort. Okay, and that we're not going to do in this clip, but in the next one, using an analog of what's called the second derivative test. We're going to somehow, using second order partial derivatives, be able to say, hey, this is neither. This is a minimum. This is a maximum. This is neither, or something like that. Okay, if I remember correctly, only this one turns out to be a minimum. Okay, and the other are imposters. Clear? Good? Everybody? Okay. Do you agree, by the way, that looking at this function, it would have been hard to argue in terms of, just kind of abstract thinking that this point is a minima for that function? Right? Okay, so we need the more mathematical machinery here. Okay, so coming up next, how do we sort critical points? Second derivative test, and what we're going to do, the main tool to obtain that second derivative test is going to be using the Taylor polynomial. Of order 2, don't panic. Okay.